In the previous video, we talked about how chemistry is the study of matter. So what is matter? Well, what exactly is all of the stuff around us, as well as the changes that matter undergoes? So we observe that matter can melt, freeze, boil, combustion, so wood transforms into a gas, and in the process gives off a lot of heat. Okay, and in the previous video, we also talked about the categories that all matter is organized into. So now, next in this video, we're going to talk about the two categories that properties of matter, or the changes that matter undergoes, fall into. Okay, so I think we all inherently know what a property of something is. It's just like an attribute or characteristic, and typically something that can be measured. So how heavy something is, how strong it is, or maybe how toxic it is, how reactive it is. Maybe its color, its smell. These are all properties or characteristics. And specifically, we're thinking about of matter, different kinds of matter around us. Okay, and then obviously a change of matter is when something about the matter, okay, and then obviously a change of matter is when something about the matter is changing in some way. Okay, so a property of matter, or a specific change that some matter undergoes, is either going to be classified as physical or chemical. So a physical property or a physical change, or a chemical property or chemical change. Okay, so if a property of a substance can be measured or observed without changing the composition or identity of the substance, which you can interpret this as meaning that no chemical reactions are taking place. It's the same idea. If the composition or identity of a substance doesn't change, then no chemical reactions are taking place. That's the essence of a chemical reaction. You're going from one type of substance or substances to another type of substance or substances. Okay, so if we're thinking about a property of matter to where no chemical reaction takes place in order to observe or measure this property, there's no chemical reaction that has to take place in order to observe or measure this property, then it's a physical property. Okay, so this copper round bar stock here, this matter has a color, it's going to have a smell, a strength, a ductility. This rubber here, same idea. Color, smell, certain amount of flexibility, strength, ductility. Any characteristic that you can possibly think of where in order to observe or measure that characteristic, a chemical reaction doesn't have to take place, right? All of the properties that I just stated, if you think about it, to observe or measure those properties, no chemical reaction needs to take place. Melting points, boiling points, electrical conductivity, thermal conductivity. So you might say, well, wait a minute, not a melting point or boiling point, because isn't a change taking place? Don't we need to melt the copper and boil the copper? Same idea with the rubber. Yes, but when a substance melts or boils, its composition, its chemical composition, what the essence of what it's made of doesn't change, right? If you melt or you freeze or you boil water, it's still H2O in all of those phases. The chemical composition doesn't change. When something melts, no chemical reaction is taking place. Okay, a physical change is a similar idea to a physical property in that you have matter undergoing some change, but there's no chemical reaction taking place. So if the matter melts or it boils, a change is taking place, right? But there's no chemical reaction that's happening during that change. Here you've got water condensing. Here you've got sugar dissolving in coffee. The dissolving process, there's no change in the chemical identity of the substance. It's just they just mix together. You still have it's sugar molecules, and you still have all the intact coffee, which is primarily water molecules. Okay, now what you can think about is that any physical change is going to be associated with a physical property. directly associated with a physical property, right? So this water condensing out of the air, that's going to be associated with the boiling point of water, right? The temperature in which H2O changes from gaseous to liquid. In cases like this, it's a little more complicated because the air is sort of saturated with water vapor, so condensation, it's not like it's having to take place at like 100 degrees Celsius, but that's the idea. At some point where the phase change of the water happens from gas to liquid. Here, the corresponding physical property would be solubility, how soluble the sugar is. Okay, now there's also chemical properties and chemical changes. A chemical property of a substance is a property that cannot be observed or measured without carrying out a chemical change. A chemical reaction needs to take place. A chemical reaction involving the matter you're analyzing needs to take place in order to observe or measure a chemical property. So the flammability or the toxicity of a substance are chemical properties. In general, you can't determine how flammable a substance is without combusting that substance. Toxicity describes a substance's intrinsic ability to cause harm or adverse effects when that substance is digested. And so you might say, well, couldn't you potentially quantify toxicity before letting any living organism ingest the substance? Yes, but the property itself is based on chemical reactions taking place. The organism ingests the substance, and the chemical breakdown and resulting processes result in the deadly effects, right? The property is intimately tied to chemical reactions taking place, just like flammability is. Okay, so chemical properties are, again, flammability, toxicity, the ability to burn, so like reactivity, acidity or basicity, corrosiveness, etc. Okay, now a chemical change is a change of matter that is directly associated with a chemical reaction or a change in composition taking place. So iron changing from iron to rust, iron oxide, the rotting of a banana. These are chemical changes. These changes are as a result of a chemical reaction. Okay, other chemical changes would be the whole burning process, combustion of wood, baking a cake, digesting food, souring milk, etc. Now, what you can think about is one difference between a physical property and a chemical property is that you can measure a physical property without a physical change taking place, without needing a physical change to take place. But that's not the case with a chemical property. If you think about it, you can't measure or observe a chemical property without a chemical change taking place, but not for a physical property, right? You could observe the color of a substance, but no physical change took place. But you can't really observe or directly measure a chemical property without the chemical change occurring. Okay, one way we can get an interesting perspective of physical properties, but I think this also helps to give us some intuition on properties of matter in general, chemical or physical, is by looking at different ways in which mixtures are separated. So if you think about the definition of a mixture, as we talked about in the previous video, mixtures or the mixing process it's all physical. So sugar mixed in water is a homogeneous mixture, right? So, for example, sugar mixed in water, as we talked about, is a homogeneous mixture. But it's all physical. No chemical changes take place. The sugar molecules are fully intact. They get broken up from the clumps, but no chemical change takes place. So, and that's what a mixture is, any kind of mixture. It's when two substances are combined together, but the substances retain their physical identities. Okay, so as a result, what you can think about is mixtures are separated using physical processes or processes that take advantage of the physical properties of the substances contained within the mixture. That's how the substances are separated. Okay, two examples of how mixtures are separated are with the processes of filtration and distillation. Okay, so filtration, everyone knows what filtration is. Here's a more sort of precise laboratory filtration setup, but it's still just at the end of the day, you have this funnel with filter paper laid inside, and you pour this. It's a mixture of liquid and solid. The liquid passes through the filter paper, the solid can't, and the solid residue left. And what you're left with is the filtrate, just the liquid, and the solid remains behind on the filter paper, right? We use filtration when cooking, separating the spaghetti noodles from the water. Okay, so in general, what type of mixture, a homogeneous mixture or a heterogeneous mixture, would you say that filtration is used to separate the components? Well, in the previous video, I gave a rough definition of homogeneous and heterogeneous mixtures. A homogeneous mixture, I mentioned that you can think about as being mixed thoroughly well to where all components are uniformly distributed. And that is a correct definition, but to be a bit more specific, in a true homogeneous mixture, the components are uniformly distributed down to the molecular or atomic level. Air is a homogeneous gas mixture of primarily oxygen and nitrogen. And you can imagine this distribution is uniform down to the molecular level of every O2 and N2 molecule. With liquid or solid homogeneous mixtures, a solute is dissolved in a solvent. The dissolving process is happening at the molecular level. Sugar dissolving in water, for example, each sugar molecule is becoming fully hydrated or fully surrounded by water molecules. We'll talk about the details of the dissolving process later in chapter 4, but the idea is with any homogeneous mixture, the components are mixed thoroughly well down to the molecular level. Okay, but with heterogeneous mixtures, this isn't the case. With a heterogeneous mixture, dissolving or a molecular or atomic level distribution of the components of the mixture doesn't take place. Okay, so with that, what you can think about is the filtration process, in general, is only going to be effective on heterogeneous mixtures. Why? Because the dissolved particles in homogeneous mixtures they're too small. And even at the same time, in some cases, they're too intimately connected to the solvent particles, like sugar and water, for example, to be separated using filtration. So filtration is only, in general, is only effective for separating insoluble solid particles from a liquid or gas in a heterogeneous mixture. Okay, now, but what physical property, let's think about what physical property is filtration taking advantage of to separate substances. Okay, so filtration is taking advantage of, you could say, depending on how you look at it, you could say the size or the solubility properties of substances, or you could look at it, so in this example here, or the spaghetti noodles in water example, is taking advantage of the different states of the matter. One is a solid and one is a liquid at the room temperature and pressure conditions. Okay, now distillation is another method used to separate mixtures of substances. So with distillation here, you've got, as an example, you have salt water. So you're trying to separate the salt from the water. This is heated up. The water evaporates. The pressure builds. Some of the steam is forced down here into this condenser where you've got this coolant. They say cooling water, or whatever. It's a coolant to make this region here cold, relatively cold from the steam. So now water condenses in this region. It's forced down by gravity down the tube, and it comes into this distillation flask. And now it's pure water. And what's left behind is, when the process is done, is salt. Okay, now, in general, what types of mixtures is the distillation process used to separate the components? Well, in this case, it's going to be homogeneous mixtures, right? Salt water is a homogeneous mixture. You can just think about why, compared to something like filtration, the distillation process is more effective at separating a homogeneous mixture. The whole evaporation process is really molecule by molecule. All right, so what physical properties of the substances is distillation taking advantage of? Well, the boiling points of the substances, right? The different boiling points. Water boils at a much lower temperature than salt. You can still boil salt. It's an ionic compound. It's going to have a very high boiling temperature, but it has a boiling temperature, but the boiling temperature of water is a lot lower. Okay, chromatography is another technique used to separate homogeneous mixtures. Okay, but chromatography takes advantage of different physical properties than distillation. So here, column chromatography takes advantage of the polarity of different substances. So the uneven charge distribution, like water. Water is a polar molecule. You have more of a negative charge on the oxygen and more of a positive charge on the two hydrogens. So in column chromatography, you put the substance, the mixture to be separated into a column. And within this column, packed in are these polarized beads. And the more polar components of the mixture don't travel as far down the column. And so you get the separation of the components. Okay, with paper chromatography, you dip one end of a paper into a solvent. The solvent is below the starting line, but capillary action causes the solvent to climb up the paper over time, slowly over time. Okay, now at the starting line, you have a sample of the mixture you want to separate. So then the solvent eventually climbs up over the starting line, and the mixture dissolves into the solvent, but certain components have more of a propensity to adhere to the paper, and so don't travel as far up the paper. And so then you get the separation of the components. Now you also have gas chromatography to separate mixtures of gases, homogeneous mixtures of gases. So you've got this carrier gas, and here the gas mixture to be separated is injected. The carrier gas carries the gas mixture through this chromatography column, which has a liquid in it. Once again, because of the differences in polarity of the different substances, there's a separation. You have a detector, and then you can read out on the CPU the different components in the mixture.